Hey everyone. So today we're talking about section 3.6, which goes over differentials and how we can use differentials for quick and accurate approximations. Increments in x and y. An increment in x is the change in x, which we denote by delta x. So you may be familiar with this notation in science, but we're going to use it pretty frequently in here too. And the increment in y is the change in y, which again is going to be delta y. So just for some clarity, the triangle delta there, it's not a variable, it just stands for the change in. So we could also have like delta z's, delta a's, whatever we need. Delta is just saying the change in a variable. So if we take a look at the function y equals f of x, which equals x cubed, if x changes from 2 to 2.1, find delta x and delta y. So delta x is the change in x. If we're going from 2 to 2.1, then 2.1 minus 2 is 0.1. X changed by a factor of 0.1. Delta y, so the change in y is what would happen if we plug in the values of x. So if I plug in 2.1 into f of x, I'll get f of 2.1 minus f of 2. The function is x cubed, so this would be 2.1 cubed minus 2 cubed, which we're going to need a calculator for this, but 2.1 cubed is 9.261, 2 cubed is 8, and then the difference is 1.261. So when x is 2, if I increase it by 0.1, my y value will increase by 1.261. And those would be our delta x and our delta y for this scenario. In example 2, it says that y equals f of x, which is equal to x squared over 2. And for part A, they want us to find delta x, delta y divided by delta x when x1 is 1 and x2 is 2. So starting with delta x is going to be equal to x2 minus x1, which is 2 minus 1, which is 1. So the change in x is 1. Delta x equals 1. So to find delta y, the change in y would be f of x2 minus f of x1. So that's f of 2 minus f of 1. So I'm going to have to plug in for x squared over 2. So this is 2 squared over 2 minus 1 squared over 2. And this would be 4 over 2 minus 1 over 2, which is 3/2. So my delta y is 3/2 or 1.5. And then for part 3, they say, what is delta y divided by delta x? So delta y over delta x is 3/2 over 1, which would be 3/2. So for part 2, they say find f of x1 plus delta x minus f of x1 all over delta x when x1 is 1 and delta x is 2. So this looks harder than it really is. I know all these values, so it's going to be f of 1 plus 2 minus f of 1 all over 2. So this is f of 3 minus f of 1 divided by 2. So f of 3 is going to be 3 squared over 2. I'm just plugging into the function in the top. So this is 9/2 minus 1/2 all over 2. So 8/2 over 2. Well, 8 over 2 is 4, so I'm going to get 4 over 2, which is 2. So in that example, you may have realized that it kind of looked like we were doing a difference quotient, like the f of x plus h minus f of x over h. But instead of referring to the change in x as h, we were calling it delta x. So if we replace all the h's with delta x, then we have essentially the exact same thing. So this is really our delta y over our delta x. And if we wanted to take a look at our derivative, the derivative would be defined as the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x, meaning that the derivative is the limit as delta x approaches 0 of delta y divided by delta x, assuming that the limit does exist. So assuming that the limit exists, then for very small values of delta x, the difference quotient delta y over delta x provides a very good approximation for f prime. So I'm saying that delta y over delta x is approximately f prime of x as long as delta x is very small. Therefore, if we already know what delta x is, we can say the change in y is approximately the derivative of f times delta x. And the smaller our delta x is, the closer our approximation will be. So this brings us to the differential. So if y equals f of x, and it's differentiable, then the differential dy or df is defined as the product of f prime and dx. And dx is going to be equal to delta x symbolically. So I can say that dy equals f prime of x dx, or df is f prime dx, as long as dx equals delta x. They also want us to know that dy or df is actually a function involving two independent variables. We have x and the change in x. If one or both of those variables change, then dy or df will also be affected. So in this example, they say find dy if f of x equals x squared plus 3x, and they tell us that x equals 2 and dx equals 0.1. So remember, dy equals f prime of x dx. So the first thing I need to do is I do need to take the derivative of f. So f prime of x is 2x plus 3. So dy is going to be 2x plus 3 dx. And then they tell me that x equals 2 and dx equals 0.1. So I get 2 times 2 plus 3 times 0.1. So this is 7 times 0.1, meaning dy equals 0.7. B, same thing, but they want x to equal 3 and dx to equal 0.1. So I still know that dy is 2x plus 3 dx. And I'm just going to plug in 3 and 0.1. So I'm going to get 2 times 3 plus 3 times 0.1. So this is 9 times 0.1. So dy is going to be 0.9. And for C, they say let x equal 1 and dx equals 0.02. So that means that dy equals 2 times 1, which is 2, plus 3, which is 5, times 0.02. And that will give me 0.1. Example 4. So this is just like our other example. They say that f of x is the square root of x plus 3, and they want us to find and evaluate for dy. So in A, they're telling us that x equals 4 and dx is 0.1. So the first thing I need to do is I do need to take the derivative of f. So f of x, I know it's the square root of x, but I'm going to write this as x to the 1/2 plus 3. I can take f prime. It's going to be x, or it's going to be 1/2 x to the negative 1/2. The exponent comes down, we decrease the exponent by 1, And this is 1 over 2 square root of x. So when I want to find my dy, I know that dy is defined as f prime of x dx. So dy is going to be 1 over 2 square root of x dx, and they tell me that x is 4 and dx is 0.1. So dy is going to be 1 over 2 square root of 4 times 0.1. So this is going to be 1 over 2 times 2 is 4 times 0.1. So that's going to be 0.025. So for b, it's the same thing, but we're plugging in 9 and 0.12. So dy is going to be 1 over 2 times the square root of 9, which is 3. 2 times 3 is 6, times 0.12. And for that one, we'll probably need to use a calculator. Let me find a calculator. So it's 0.12 times 1 over 6. That's the same thing as dividing by 6. And we're going to get 0.02. And then they say let x equal 1 and dx is 0.01. So the square root of 1 is 1, so it's going to be 1 over 2 times 0.01. So that's going to be 0.005. On this slide, we want to talk about how we can use differentials to find an approximation. So we said that delta y over delta x is approximately f prime of x, meaning delta y is approximately f prime of x times delta x. And of course, this works better the smaller we have for delta x. And this is very similar to our differential dy equals f prime of x dx. So we can say that delta y is approximately dy. Again, the smaller our delta x gets, the closer we are to dy. We can say that delta y and dy are similar for this very reason. If we're taking a look at this function, y equals f of x, and we have a point where I'm going to draw a tangent line. This tangent line and this curve are very close when our delta x is very small. So for this example, here's our delta y, here's our dy, and we can tell that delta y is much, much bigger. But as we shrink our delta x, the difference becomes smaller and smaller. You can see here the 2 points are getting closer and closer and closer together. So for small values of delta x, our delta y should be approximately dy, or our derivative. So now we're going to take a look at how the approximation and the actual value will be very similar. So it says let y equal f of x, which is 6x minus x squared. And they say find delta y and dy when x equals 2. So we're going to see that one of these ways is going to be a little bit longer than the other, but the final results will be very close. So delta y, we know that delta y equals f of x plus delta x minus f of x. And on this right-hand side, we know that dy equals f prime of x times dx. So let's go ahead and do the dy first because this is really fast. We know that the derivative of f is going to be 6 minus 2x. So dy is going to be 6 minus 2x dx. And they told us to go ahead and plug in 2 for x. So dy is going to be 2 dx. 2 times 2 is 4, 6 minus 4 is 2. So dy is 2 dx. So however much x is changing by, multiply by 2, and that's our dy. So let's go look at our delta y. So I can plug in 2, just like I did on the other side. I'm going to get 2 plus delta x minus f2. But now for f of 2 plus delta x, I'm going to have to plug in into f of x, and wherever I see an x, I'm going to replace it with 2 plus delta x. So this will give me 6 times 2 plus delta x minus 2 plus delta x squared minus, if I plug in 2, 6 times 2 is 12, minus 2 squared, 4, so 12 minus 4 is 8. So let's clean this up a little bit. I'm going to get 12 plus 6 delta x minus 2 plus delta x squared is going to be 4 plus 2 times delta x plus delta x squared minus 8. So the 12 and the 8 are going to reduce. We're going to get 4 plus 6 delta x minus 4 delta x minus delta x squared. And I can, again, combine some like terms. The 4 and the negative 4 cancel out. 6 delta x minus 4 delta x is going to be 2 delta x. And then I have a minus delta x squared. So this is our delta y. And if you take a look, we get 2 delta x minus delta x squared versus 2 dx. And now we always say that dx and delta x are going to be the same. So the only real difference between the two is this minus delta x squared. Now, keep in mind that if delta x is very small, then delta x squared is extremely small, meaning these should be very similar answers, and finding dy was very quick, where delta y took some time. So let's actually plug in some values and see what we get. So they say compute delta y and dy if delta x is 0.1, 0.2, and 0.3. So we're going to get 3 different answers. So if I plug in 0.1, I'm going to get 2 times 0.1 minus 0.1 squared, and that is going to be 0.19. If I plug in 0.2, I'll get 2 times 0.2 minus 0.2 squared, and this will be 0.36. And if I plug in 3, I'm going to get 2 times 0.3 minus 0.3 squared, and this will give me 0.51. So let's check our dy's. So our dy, we're just plugging in right here, and I'm going to get 3 answers, and we can then compare. If I plug in 0.1, I'm going to get 0.2, 0.4, and 0.6. So let's compare. 0.19 compared to 0.2. That's very close. For the second answers, 0.36 and 0.4, it's a little bit further apart, but they're still pretty close. And then for our third one, 0.51 and 0.6, again, a little bit further apart, but they're pretty close. And again, this is when dx gets smaller, these answers will get closer and closer and closer. So the real question is, how accurate do we need to be? Do we need the exact answer, or will an approximation work? Because finding the approximation over here is very quick. Here we have another example where we're going to be comparing our delta y's and dy's. So they say find delta y and dy when x equals 4. So again, I'm going to split it in half. On the left-hand side, I'm going to do delta y. So delta y should be equal to f of y, or f of x plus delta x minus f of x. And they tell me that x equals 4, so I can say that delta y equals f of 4 plus delta x minus f of 4. So we need to plug into 6x minus x squared. And when we do that, we are going to get 6 times 4 plus delta x minus 4 plus delta x squared. And then we're going to subtract the f of 4. If I plug in 4, I'm going to get 24 minus 16. 24 minus 16 is going to be 8. So let's distribute the 6 in. I'm going to get 24 plus 6 delta x. 4 plus delta x squared is going to be 16. I'm going to give myself a little more room. It's going to be 16 plus 8 delta x plus delta x squared minus 8. So 24 minus 16 minus 8 is 0, so these all will go away. I have 6 delta x minus 8 delta x, so that's going to give me negative 2 delta x. And then I'm going to have a minus delta x squared. So this is my delta y. So let's check what dy is. So we know that dy equals f prime of x dx. So let's go ahead and find our derivative here. F prime of x is going to be 6 minus 2x. So dy is going to be 6 minus 2x dx. And they told us that x equals 4. So 2 times 4 is 8. 6 minus 8 is negative 2. So dy is negative 2 dx. So again, if we take a look at our two answers, delta y is negative 2 times delta x minus delta x squared, where dy is negative 2 dx. And considering dx and delta x are going to be the same thing, the only real difference is the delta x squared. Which, again, if delta x is very small, then delta x squared is going to be extremely small. So let's break down our calculator and compute delta y and dy if delta x is negative 0.1, negative 0.2, and negative 0.3. So we're going to get 3 different answers. So if I plug in negative 0.1, well, negative 2 times negative 0.1 is going to be 0.2 minus negative 0.1 squared is 0.01, giving me 0.19. If I plug in 0.2, well, negative 0.2 times negative 2 is 0.4 minus 0.2 squared, or negative 0.2 squared is going to be 0.04, which gives me 0.36. And if I plug in negative 0.3, I'm going to get 0.6 minus 0.09, which is 0.51. So I'm actually getting the exact same answers as our last example. And let's check our dy's. Well, we should get the exact same thing. We're going to get 0.2, 0.4, and 0.6. So again, if we make the comparisons, these are pretty close. Of course, the bigger our dx gets, or our delta x gets, the further our answers are apart. But the smaller our dx is, or our delta x is, the closer our answers are. So example 7, it says that a company manufactures and sells X transition radios per week. If the weekly cost and revenue equations are the cost C of X equals 5,000 plus 2X, and the revenue R of X equals 10X minus X squared over 1,000, and they say they sell between 0 and 8,000 transistor radios, I think it's a week, then find the approximate change in revenue and profit if the production is increased from 2,000 to 2,010 units per week. So if we're just going from 2,000 to 2,010, that means that our delta x is 10. 2,010 minus 2,000 is 10. And they give us our revenue. I'm going to rewrite the revenue real quick. R of x is going to be 10x minus 1 over 1,000 x squared. That'll make it easier to take my derivative later. But then they also ask for the profit, and the profit was not given to us. So profit, I'll call it P. profit is revenue minus cost. So it's going to be R of X minus C of X. And that's not too bad. We're going to have 10x minus x squared over 1,000 minus 5,000 minus 2x. So 10x is going to turn into 8x minus x squared over 1,000 minus 5,000. And I got that by taking R of X and subtracting the C of X. So if they want an approximate change, I don't need to actually find delta P and delta R. I can find dP and dR. So I'll say that the dr is going to be r prime of x dx. And I'll say that dx is 10. So I need to go ahead and take the derivative of r. So r prime is going to be 10 minus 1 over 500x. So the derivative of 10x is 10. The derivative of x squared is 2x times 1 over 1,000 is 1 over 500x. So dr is going to be, oh, and we can even plug in 2,000, because remember, we're starting at 2,000. This is our x value. If we plug in 2,000, I'm going to get 10 minus 2,000 divided by 500 is 4, minus 4. And our dx is 10. I'll get 6 times 10, which is 60. So our change in revenue is $60. So let's check our change in profit. So I need to take the derivative of the profit. So P prime. I'm going to get 8 minus 1 over 500x. And then the derivative of 5,000 is just 0. So dP is going to equal 8 minus 1 over 500x times dx, which is 10. So if I plug in the 2,000, dP is going to be, well, it's going to be 8 minus 4, which is 4 times 10. So my change in profit, or my approximate change in profit, is $40. All right, so that's not too bad. So there is more to this problem. They're going to want us to find the exact change in revenue and the exact change in profit so we can compare. And that will be on the next slide. So here they want us to find the actual change in revenue and the actual change in profit. So what we're going to do here is, I'm just going to remind us, on our last slide, we got that the change in revenue was approximately $60 and our dP was $40. That way we can compare our answers. We also need to use the profit function here. So our P of x was 8x minus x squared over 1,000 minus 5,000. So to find the actual change in revenue and the actual change in profit, our delta R and our delta P, it's just going to be R of 2010 minus R of 2000. And delta P is going to be the profit at 2010 minus the profit at 2000. And from here, it's really just plugging in. So let's get our calculator out. And for the revenue, I'm going to do 10 times 2010 minus 2010 squared over 1000. So 10 times 2010 is giving me 20,100 minus 2010, so 2010 squared. And then we need to divide by 1,000. So that's going to be minus 4,040.1 minus R of 2,000. So we got to plug in 2,000 now. 10 times 2,000 is going to be 20,000. Minus what happens when we plug in 2,000 squared over 1,000. So 2,000 squared over 1,000 is going to be 4,000. So 20,100 minus 4,040.1 minus 20,000 minus 4,000 is going to give me 59. So the change in revenue is 59.9, which if you check, our approximation was 60. So we're off by 10 cents. So we're going to get a similar result with profit. We got to plug into 8x minus x squared over 1,000 minus 5,000. So I'm going to do 8 times 2,010. So that gives me 16,080 minus 2,010 squared divided by 1,000, which is going to be minus 4040.1 minus 5,000. And then I need to subtract what happens when I plug in 2,000. So that's going to be 8 times 2,000, so that's 16,000. What happens when I plug in 2,000 into x squared over 1,000? So that should give me, I believe, 4,000. 2,000 times 2,000 divided by 1,000 is 4,000. And then we got the minus 5,000 again. So I'm going to do the top row. So I get 16,080 minus 4040.1 minus 5,000. So that gives me 7,039.9. And when I do the second row, I'm going to get exactly 7,000. So the difference is 39.9, which was the 40. So we're off by 10 cents again. So it's kind of up to us, like if you were reporting this to someone and you got a revenue change or a profit change of 59.9 and 39.9 respectively, would you just report that as $60 and $40? I know most people would. So it really depends on how accurate your answer needs to be. Because finding the approximation here was much faster and didn't really require a lot of computation, where finding the exact change did. Of course, with computers and calculators, we can find the exact answer. So this is all about the most precious resource of your time. Do you need to be exact, or will an approximation do? All right, so for the closing thoughts, so this section, differentials, it's also known as linear approximation. I know when I was learning this as a student, I was always hesitant to care, because why would I want to find an approximation when I could find the exact answer? And it really boils down to just time. The approximation can be very quick, and if you don't need to be super accurate, then the approximation is fine. It's kind of like when you're taking your car in to get a repair, usually they're going to give you an estimate before the actual repair. And it's just so that people know what to expect. Is it going to be a $100 repair? Is it going to be a $1,000 repair? That's good to know, even if the final cost comes down to be $96 or $960. It was good to know which ballpark we're in, how close are we. So that's the idea. Is if we're talking about production, you're going to see that a lot in the next section. If I know that I'm going to be making more money by producing an additional unit, then yeah, it's good to know the exact amount, but honestly, I'm really just worried about the sign. If I'm making more money by continuing production, I'm going to continue production. Or if I'm going to lose money if I continue production, you better believe I'm going to halt production. In that case, the exact number wasn't as important, but rather the action of I should continue manufacturing or stopping. So hopefully this section made sense and you feel comfortable taking or using linear approximation. The next section is going to continue where we left off here, and we're going to have some more real-world application. So the homework should be posted, and just let me know if you have any questions.